Uh, Thanks, Jaime, for the introduction, and let me thank you and Lucas for the invitation. It's a great pleasure to give this talk here at the Colloquium. So this is a joint work with Wanderson Lima from Universidade Federal do Rio Grande do Sul. And as Jaime said, I'm going to talk about a two-piece property for free boundary minimal surfaces in the ball. So let me start by recalling the definition of a minimal surface with free boundary. So you have sigma, a compact surface properly immersed in the ball. We say that it's a minimal surface with free boundary if first it's minimal in the usual sense, so its mean curvature vector vanishes, and second, it meets the sphere with a 90-degree angle. So that means that the conormal along the boundary is orthogonal to the sphere. Okay. In our work, we also consider the notion of a partially free boundary minimal surface. And this is just because besides the part of the boundary contained in the sphere, we also have a part of the boundary contained in the interior of the ball. Okay? We call this part of the boundary in the sphere the free boundary, and the one contained in the interior of the ball we call fixed boundary. Okay? So you could ask, given this definition, right, why do we use this expression of free boundary for surfaces with these properties? And this is because they can be seen as a critical point of the area functional for the free boundary problem, right? If you have sigma here, a compact surface with boundary properly immersed, so you can consider a one-parameter family of immersions, okay, such that the boundary stays on the sphere, but you let it vary. So that means that the variational vector field, here we are denoted by x, is tangent to the sphere along the boundary of your surface. Okay? So when you look at the first variational formula, you get this expression. And you can see that sigma will be a critical point if and only if these two terms vanish for any x. So this will tell you that the mean curvature vector must vanish and the conormal along the boundary must be orthogonal to the sphere. And that's exactly the definition that we had in the previous slide. Right? Let me mention that these two notions of minimal surface with free boundary hold in any Riemannian manifold with boundary, not only the ball. But for this particular case of the ball, we have a third characterization that is very useful. So let me mention here. A well-known fact is that surface in the Euclidean space is minimal if and only if the coordinate functions are harmonic. And it's not difficult to check that this condition that the conormal along the boundary is orthogonal to the sphere is equivalent to the condition that the normal derivative of each harmonic function is itself. So these 2 points here will give us a third characterization for free boundary minimal surfaces. Okay, so I wrote them all here. Okay. And a very interesting and important fact to the development of the theory of free boundary minimal surfaces in the ball is that this third characterization here is connected to the Steklov problem, which is an eigenvalue problem. So let's recall it here. You have sigma, a compact surface with boundary, and you consider L the Dirichlet to Neumann map that takes a function defined on the boundary of your surface and sends it to the normal derivative of its normal extension. Okay? So this is a non-negative self-adjoint operator. It has discrete spectrum that goes to infinite, and the eigenvalues we call Steklov eigenvalues. So the eigenfunctions we call Steklov eigenfunctions. Okay. And then Ilana Fraser and Rick Shane in their paper in 2011, they showed that you have that sigma is a free boundary minimal surface in the ball if and only if the coordinate functions are Steklov eigenfunctions with eigenvalue 1. So you can see that this is exactly the third characterization that we had in the previous slide, because you can see that this would imply that the coordinate functions are harmonic and the normal derivative of each of them is itself, right? Let me remark that that free boundary minimal surfaces have been studied for a while, for instance, since Courant at least, But it was only after this observation by Fraser and Shane that many people got interested in the subject. And for the last 10 years, many people have worked on the subject, and there are many results, okay? But before talking about results, let's talk about the known examples that we know so far, at least some of them, okay? First, the trivial example, we have equatorial disks. You take any plane passing through the origin, you intersect your ball, you get this free boundary minimal surface. The second simplest example is what we call the critical catenoid. It's not difficult to get it either. You just consider the parameterization of the catenoid in the Euclidean space, right? And you can show that there is a unique piece of the catenoid that is a free boundary minimal surface in a ball of a certain radius, okay? And this radius here is exactly the unique solution to the equation T equals T, okay? Then to get our critical catenoid, we just need to rescale this radius to 1, okay? And then you get it. Although these two examples are kind of simple, we do have a lot of interesting results related to them. So before continue talking about examples, let me mention some of the results that are connected to them, okay? So first we have this result by Nietzsche from 85. He proved that the equatorial disks are the only free boundary minimal surfaces in the ball with the disk topology, okay? So we have this unicity. And here I would like to mention that there is an analogy between free boundary minimal surface in the ball and closed minimal surfaces in the sphere. So for instance, this result, and this analogy has guided the results in the area. Okay, so for example, this result by Nietzsche is the analog that says that the equatorial spheres are the only minimal spheres in S3. Okay, so we'll keep talking about this analogy here. Okay. Okay, but so we have this unicity result by Nietzsche. Okay, so it's natural to ask if we also have the unicity for the critical catenoid, right? Is the critical catenoid the only free boundary minimal surface in the ball with the analogous topology? And this is a well-known conjecture by Ilana Fraser and Martin Lee, which is still open, although we do have some particular cases that are known, and we'll mention a couple of them at the end. Okay, and thinking about the analogy, you can see that this conjecture is the analog of the Lawson conjecture, which was proved by Brendel, and says that the Clifford torus is the only embedded minimal torus in S3, right? Three different groups of people proved independently, Devido, Tran, Graham-Smith, and the Tang-Zhu, they show that the index of the catenoid is 4, right? And there is a very interesting problem related to this result, which is to show that the critical catenoid is the only example of free boundary minimal surface in the ball with index 4, right? And this problem here would be the analog of the result by Urbano. If you remember, Urbano proved that the Clifford torus is the only closed minimal surface in S3 with index 5, right? So it's a characterization of the Clifford torus by the index, right? And this problem has caught the attention of many people because if you recall the proof of the Wilmer conjecture by Marx and Menezes, you recall that one of the main points in their proof is to use the characterization of the Clifford torus by its index. So it's natural to think that if you want to prove the analog of the Wilmer conjecture in the free boundary context, a characterization of the critical catenoid by its index might be important. Okay, good. So let's go back talking about examples. Okay, so in their paper in 2012, Fraser and Shane, they constructed a family with genus 0 and k boundary components. K here, any integer, but as you can expect, for k equals 1, they recovered the equatorial disk, right? We do have unicity. And for k equals 2, they recovered the critical catenoid. So for k greater than 3, they got new examples, okay? The proof is very sophisticated, but I can just give a rough idea of the proof. So what they did was, very roughly speaking, you consider sigma a compact surface with boundary with this topology. So here genus 0 and k boundary components. And given any metric on your surface sigma, you look at the quantity. The first is Stekelov eigenvalue of sigma with respect to the metric times the length of the boundary, also with respect to the metric. So Fraser and Shane were able to prove that the maximum of this quantity is attained by a smooth metric, and sigma endowed with this metric can be realized as a free boundary minimal surface in the ball. Okay, so here is the rough sketch of what might look one of the elements of this family for k large, because they also prove that when k goes to infinite, the elements of this family converge to an equatorial disk with multiplicity 2. So it's natural to believe that for k large, you can see an element of this family as a connected sum of 2 parallel disks near each other and glued by something like half catenoids. Okay. There are many other examples that were constructed using gluing techniques or min-max theory. We are going to mention a few here. Okay. So first we have this result by Abigail Folha, Frank Paccard, and Tatiana Zolotareva. Using gluing techniques, they constructed 2 families, one with genus 0 and one with genus 1, both for k large. And it's expected that this family of genus 0 coincides with the family by Fraser and Shane, although we don't have proof. Okay. And this, for this family here with genus 1, an element here you can think as if you take an element from the genus 0 and you put a neck right in the middle. Okay. Dan Kedover, using min-max theory, he constructed some examples that seem to be the analog of the Costa-Hoffman mix surfaces. So that would be the desingularization of the critical catenoid with the equatorial disk. And here he needs the genus to be large. So it's still an open problem to get these surfaces for any genus. So for example, it would be very interesting to get the analog of the Costa surface, right? Genus 1. And Capuleas and Lee, using gluing techniques, they constructed a family with the same topology as Kedover, and it's also expected to be the same, but no proof yet. Okay. In the same paper, Kedover also constructed some examples with symmetries of some of Platonic solids like the cube, the tetrahedron, and dodecahedron. Here would be the sketch of the one with the cube symmetry. And again, using gluing techniques, Capuleas and Weigel constructed examples with one single component in the boundary and large genus. And these examples here are kind of interesting because if you recall the unicity result by Nietzsche, he had genus 0 and one single component is necessarily the an equatorial disk. So you could ask if this result is still true if you remove this topological assumption here. But the examples by Capuleas and Weigel show that no, we have many other examples besides the equatorial disk. Okay, and it still remained open to show the existence for any genus, and that was recently proved by Carlotto, Franz, and Schutz. They constructed that. Okay, so as we can see, the theory of free boundary minimal surfaces in the ball has developed a lot, and it has a great variety of examples. Right? So now let me talk about the two-piece property, right? Thinking about the analogy, we have free boundary minimal surfaces in the sphere and closed minimal surfaces in S3. So here we have this result by Antonio Ross that is exactly the two-piece property in S3. So he proved the following. You have sigma, an embedded closed minimal surface. Then for any equatorial sphere, which is just the intersection of S3 with any hyperplane of R4 passing to the origin, right? So he proved that either your surface coincides with the equatorial sphere or the equatorial sphere divides your surface in exactly 2 components, and that's why we call two-piece property, okay? This result, besides being very beautiful, it gives evidence to a conjecture by Yau, which is about the first eigenvalue of the Laplacian. The conjecture is still open and says that if you have an embedded closed minimal surface, then the first non-zero eigenvalue of the Laplacian is 2, okay? And we say that the result by Ross gives evidence to this conjecture because if we assume that this conjecture is true, we can prove the two-piece. And for that, we just need to use the Courant's nodal domain theorem. So if I put in here Courant, nodal domain, we can prove the two-piece, okay? And recall that this result by Courant says that any eigenfunction of the first eigenvalue of the Laplacian has at most 2 nodal domains, right? And how do we see this? How can we prove the two-piece using the conjecture by Yau? Well, if you want to prove the two-piece, you have an equatorial sphere, right? So you can take a normal vector to the plane that defines your equatorial sphere, and you can consider the height function on your surface with respect to that plane. Okay? Then you can show that the Laplacian of this height function is exactly twice itself. So if the Yau's conjecture is correct, this is exactly the first eigenvalue. So this means that phi here is an eigenfunction for the first eigenvalue. So this means that we can apply Courant. And then we have that phi has at most 2 nodal domains. So the number of connected components where phi is positive or negative is at most 2. So from that, you get the two-piece. Okay, so since the proof by Ross is independent of Yau's conjecture, we say that it gives evidence to it. Okay, so thinking about the analogy between free boundary minimal surface in the ball and closed minimal surface in the sphere, Vanderson and I started to think whether the two-piece property would hold in the free boundary context. And we showed that it does hold, and we proved the following. So here we have M, a compact embedded free boundary minimal surface in the ball. Then for any equatorial disk, we have that either our surface coincides with that disk or the disk divides our surface in exactly 2 components. And that's exactly the analog of Ross' result. Here in the free boundary context, we also have the analog of Yau's conjecture. That's the conjecture by Fraser and Lee. And it says that the first non-zero Steklov eigenvalue for any compact embedded free boundary minimal surface in the ball is 1. Okay. So as for the Ross result, our two-piece also gives evidence to this conjecture by Fraser Lee. And the argument is basically the same. If you want to prove the two-piece, you have your equatorial disk, you can take your normal vector here to the plane, you define your height function on the surface that you want to prove the two-piece. Since M here now is a free boundary minimal surface, you get that the Laplacian is 0 and the normal derivative is itself. So if the conjecture by Fraser and Lee is correct, 1 here will be the first Steklov eigenvalue, right? And then we just need to apply the analog of Courant's result, which we also have here in the free boundary context. So it's the analog of Courant's, and again, you are going to get the two-piece. Okay, good. So now I just wanted to give the idea of the proof. You're going to see that the proof has basically 2 components. One part where the arguments are quite geometric, and another part which is more delicate, very technical, that we need to use geometric measure theory and work with currents and prove regularity. Okay, so, but here I will just give the idea. Okay, so we want to prove the two-piece over here. And what do we have? We have M, a free boundary minimal surface, and we have D, the equatorial disk. So we want to show that if they are different, if they do not coincide, then the disk divides M in exactly two components, right? The first observation is that if M is an equatorial disk, then this result is trivial, because then we would be dealing with two disks in the Euclidean space centered at the origin, and of course the two-piece will hold. Okay, so we can start the proof by assuming that M is not an equatorial disk. Okay, so we assume that M is not an equatorial disk, and we suppose by contradiction that the disk divides M in more than two components. Okay, so the proof is by contradiction. Okay, so here you can suppose that D is the horizontal disk. So if it divides in more than two components, in the upper half ball or lower half ball, you're going to see at least two components, right? So to simplify the picture in our head, you can always think about the upper half ball without loss of generalities. Okay, so in the upper half ball, we have at least two components. Okay, good. So our first step is to consider a solution to a partially free boundary problem. So how do we do that? We call MU1 one of these connected components of M minus the disk. So above, so let me draw something here. So we are assuming that here's our disk D, and we are taking one of these connected components. Like that. Then you have the fixed boundary and the free boundary. So we have gamma S and gamma I. Our first remark is that both boundary, the free boundary and the fixed boundary, are non-empty necessarily. And this is just a consequence of the maximum principle with equatorial disks. Okay, so we can show that both of them must be non-empty. And this is true for any connected component of M minus the disk. Okay, just because they are in a half ball. Okay, so we are going to use this fact right at the end of the proof. So let's remember that. Okay, good. And by construction, of course, the fixed boundary is contained in the disk D. We need to remember that. Okay, so Ilona Fraser and Martin Lee also showed that any embedded free boundary minimal surface divides the ball in two regions. So we are going to call one of these regions W and the other one W prime. So for instance, if your surface is the critical catenoid, you can see that we have a region here inside the catenoid, you can call it W. And then you have the other region around the waist of the catenoid that you can call W prime. Okay, and we are going to work with each of these regions separately. Okay, we are going to work on W and then we work on W prime. Observe that your free boundary minimal surface, the catenoid in this case, is containing the boundary of each of these regions, right? So you have that M is containing the boundary of your region W prime, W and W prime as well. Okay, and what is this partially free boundary problem that we're going to consider? So let's fix W, okay? Let's work on W first. So we are going to look at all surfaces contained in W such that it has the same fixed boundary as this component that we picked, and the free boundary will either vary in the sphere, the part of the sphere that is contained in your region W. It could even be empty, it's free, okay? And then among all such surfaces, we want to find the one with least area. Okay? Now, how do we make sure that we have a solution for this problem? And that's the point where we need to use geometric measure theory, work with more objects like currents, and then prove regularity. It's in this point where we need to make sure that this problem makes sense, that the proof becomes more technical, okay? But what is the idea? So here we'll be dealing with currents. If you haven't worked with currents before, you can keep thinking as a surface, okay? So we are going to consider this class of currents such that the support is contained in your region W, and such that the support of the boundary has two pieces. You have a piece that coincides with the fixed boundary of M1, and then another piece that is free to vary in the part of the sphere inside your region. Okay. Observe that M1, the connected component M1, as a current is contained in this class, so it's non-empty. And then we can use classical results from GMT to guarantee the existence of a minimizer for the area. Okay. Let's call sigma the support of this minimizing current. And here we prove a kind of a maximum principle that is inspired by a work of Brian White and using the notion of varifolds. We prove that either sigma is entirely contained in the boundary of the region W, or their intersection is just the boundary of sigma. And once we have this result, we can use regularity theory to get that sigma is actually a compact embedded partially free boundary minimal surface with fixed boundary exactly gamma I, of course, by construction, right? And also sigma is smooth away from possible singularities, isolated singularities of the fixed boundary and the corners. I'm going to explain in a minute what I mean by that, okay? I just want to mention that this is the most delicate part. You know, this regularity part is the most delicate one. To get the result as I wrote here, we had to combine the work of many people. So for instance, to get regularity in the interior points, we use classical results by De George and Federer. To get regularity at the free boundary points, away from the corners, we use Grutte, and for points in the fixed boundary, away from the corners and the singularities, we used Hart-Simon and also a recent result by Nick Edelin. Okay, good. Now let me explain what I mean by these singularities and corners. So if you recall how we start the construction, we had our free boundary minimal surface M, and we intersected with the equatorial disk D. So we have two minimal surfaces, and we know that the intersection of two minimal surfaces is given either by a simple curve if the intersection is transversal, or it's given locally by any pronged singularity if they are tangent at this point. So since the fixed boundary of your component M1 is contained here in this intersection, it can come with some any pronged singularities. Okay, so these are the ones that we mentioned here. Okay, and the corners, well, corners are just the points where the free boundary meets the fixed boundary. Okay, so for instance, if you have your critical catenoid and you intersect with a vertical equatorial disk, you're going to get a component whose boundary looks like this, something like that. So you have two pieces in the fixed boundary, two pieces in the free boundary, and those 4 points here are the corners. Okay, good. So the combination of all this work gives us regularity away from these any-pronged singularities and the corners. And as our contribution to this part, to this regularity part, Vanessa and I also proved that actually sigma is also regular at the corners. Okay, and for that we followed a sketch by Grutter and Simon. So we only miss regularity at these possible any-pronged singularities, right? But that won't be a problem for us because, as we are going to see, we just need regularity outside the disk D, okay? Good, so we have sigma is smooth, at least away from these any-prongs. So our next step is to show that each component of sigma is contained in an equatorial disk. That could be a priori different from our disk D, okay? And to show that, well, we use that sigma is minimizing, so we can show that it's stable. And then using the stability inequality, we can show that it's actually totally geodesic, okay? And for here, we just need to take F as the height function with respect to the equatorial disk D. And for the cases where sigma has isolated singularities in the fixed boundary, we work with a perturbation of the height function using cutoffs, okay? So we are good. And well, so each component is contained in equatorial disk. And our next step is to show that actually it must be the disk D that we started with. Okay. Am I going too fast? So we have seen that either sigma, this was the maximum principle that we proved, right? So we have that either sigma is entirely contained in the boundary of our region, or the intersection is just the boundary of sigma, right? Okay, so first observe that this case here cannot happen, because if you recall, our free boundary minimal surface is contained in the boundary of W. And since sigma is totally geodesic, is a piece of an equatorial disk, the maximum principle would imply that our surface M is an equatorial disk, but we are assuming it's not. So this first case here cannot happen, okay? So it only remains for us to analyze this case over here. So here, let's remember the boundary of sigma is composed by gamma I and gamma S, fixed boundary, free boundary. The fixed boundary is exactly, by construction, is the fixed boundary of the component M1, right? That we know is contained in our disk D. And this free boundary, we don't have information. It could be empty, okay? But that's the important thing. So sigma is totally geodesic and the fixed boundary is contained in D. So we know that for any, if this represents the disk D, if any component of sigma that is bounded by something that is not a diameter, it must be a piece of D, right? So we have that. Each component that is not bounded by a diameter is contained in our disk D. So it only remains to analyze what happens for components that are bounded by a diameter, because in this case, we could have something like this. If this represents our disk D and we have a diameter here, our component of sigma could come from, another disk here, right? Okay, and we want to show that this is not possible. And to prove that, what we're going to do is to rotate this component here around this diameter, and we're going to apply the maximum principle with the boundary of the region W, okay? And here is a little bit delicate because we have to apply 4 different versions of the maximum principle. So we might need to apply, let me change the color. We might need to apply the maximum principle for points in the interior, for points in the boundary, both fixed and free boundary, but we also need to apply the maximum principle at the corners. These 3 possibilities here are kind of classical, no problem, but for this special case where we are dealing with a maximum principle at the corner, we need a special result that was proved by Sahin, and we put all the details in the paper showing that we can use in our case, okay? So the maximum principle will say that this case cannot happen exactly as in the first case, okay? So we do have that the surface that we constructed, sigma, is entirely contained in the disk D, okay? So how would we finish the proof, right? We worked on W and we got sigma contained in D. So what we do now is we work with W prime, do the same arguments, and we're going to get another surface sigma prime. And with the properties of sigma and sigma prime, we can show that the union of them is the whole disk D, okay? And this implies that when we look at the intersection of our M with the disk D, we only see the fixed boundary. There is no other thing, right? So this means that any other component of M minus the disk, that here we are denoted by M2, would have to have empty fixed boundary, could not get to the disk D. But as we said right there in the beginning of the proof, this is not possible by a simple application of the maximum principle, okay? So with this contradiction, we get the 2-piece result, okay? Excellent. So using similar arguments, we also proved this other theorem that is the analog of another result by Ross. And it says the following. Here, W is another thing. W, now it's a compact and connected region such that the intersection of its boundary with the interior of the ball is smooth, mean convex, and intersects the sphere orthogonally. And we proved that if this region contains a diameter that is homologically trivial, then it has to be the half ball, no other possibility. Okay, good. Now, in the last couple of minutes, I would like to talk about some applications of this two-piece result. Okay. First, we have a topological application. This is the analog of a result by Solomon in S3. It says that if you have sigma here, a compact embedded free boundary minimal surface, and you have gamma, a diameter in the ball, then we prove that either they intersect each other or they are linked. And here, linked means that we cannot deform the diameter into a point by fixing, by asking that the endpoints stay in the sphere, but gamma never touch sigma. Okay, so we cannot deform the diameter into a point, keeping the endpoints in the sphere and never touching sigma. Okay, so for example, here they are linked. And this result basically says that compact embedded free boundary minimal surfaces in the ball cannot be very complicated in topological sense. Okay. Good. And recalling the conjecture of the critical catenoid by Fraser and Lee that says that the critical catenoid is the only embedded free boundary minimal surface with the annulus topology, we do have a few particular cases. So for example, Fraser and Shane, they showed that the conjecture is true if you assume that the first eigenvalue of the annulus is 1. Okay, and McGrath showed that the conjecture holds if we assume that the annulus is symmetric with respect to the coordinate planes. Okay, and in a recent work, using our result of the two-piece property, Kuzna and McGrath were able to show that the conjecture holds if we assume that the annulus is invariant by the antipodal map. So Vandes and I, we were very happy to see this application of the two-piece property. Okay, I think I will stop here. Thank you for your attention.